Good day, student. Today we continue our lecture on BJT configuration. So, transistor configuration is a connection of transistor to get variety operation. Three types of configuration. First is common base, second is common emitter, and then third is common collector. Basically, transistor have three terminal such as collector, base, and emitter. If the base is common terminal between input and output of the circuit, so this is called as common base. Same as if the emitter is common terminal between input and output, so we call it common emitter, and then same as common collector. In this chapter, we will more focus to common emitter. So we can see here for common base, if emitter is input and then collector is output, and then this one we call is common base. Same as common emitter, where the base is input and then collector is output, and then we can see here emitter is common, and then we call this one is common emitter. Same as common collector. In this chapter, we will move more focus to common emitter. This is an example of common emitter configuration which use NPN transistor. So we can see here emitter is common for input and output terminal. So input is BE junction, and then output is CE junction. So common emitter configuration is mostly applied in practical amplifier circuit because it can give good voltage, current, and power gain. This is the input characteristic of transistor BJT, where the graph shows input current IB versus input voltage VBE for several output voltage VCE. So from the graph, we can see that IB is 0 if VBE less than 0.7, and then the transistor will on if VBE more than 0.7. This is the output characteristic of transistor BJT, where the output characteristic is more important compared to input characteristic. So the output characteristics is output current IC versus output voltage VCE for several input current IB. So three operating region, that is, first is saturation region. Here is saturation region, and then second is cut-off region. Here is cut-off region, and then the third is active region. Here is the active region. Cut-off region is both junction BE and BC are reverse bias, where IC is nearly 0 with increasing VCE. Active region is BE junction is forward bias and BC junction is reverse bias. And then IC increases drastic, although only small change of IB. Active region is the area where the transistor operates as an amplifier. So in this chapter, we will be more focused to active region. And then we also have the saturation region, where both junction BE and BC are forward bias, and then the IC increase linearly with VCE. Saturation and cut-off region areas where the transistor can also operate as switch. Beta is the one of the most important parameter for transistor BJT. It is also known as DC common emitter current gain HFE. So beta is also equal IC over IB. So we can say that IC is equal to beta IB. So beta value is in between 50 to 300 for small power transistor. So beta is sometimes also referred as HFE, the term used in transistor modeling calculation for AC analysis. Beta can determine from the output characteristic of BJT, that is IC versus VCE. So from the graph we can calculate for beta AC that is 3.2 minus 2.2 divided by 30 microampere minus 20 microampere. So the answer is 100. For beta DC can be determined using the Q point here. So that is 2.7 milliampere divided by 25 microampere, and then the answer is 108. So from the result we can see that beta AC is nearly beta DC. In the exam or our test, beta is given. This is the important equation that you must remember for your test and your final exam. In the active region, VBE is 0.7 volt, IC is nearly IE, IC is beta IB, and IE is equal to IB plus IC. And then after you solve the equation, so you can get IE equal to 1 plus beta IB. This is the circuit that the transistor BJT operates in cut-off region. So we can see that there is no DC power supply. So from the analysis, we can find that BBB is equal to 0 volt, and then BE junction is not biased or reverse bias, and then BC junction is reverse bias, and then after that we can analyze that IB is 0 ampere because no DC supply voltage, and then IC is also 0 because IC is equal to beta IB, and then if we analyze using Kirchhoff law analysis, so we can find that VCE is equal to VCC equal to 12 volt. This is the circuit that the transistor BJT is operate in the active region. So the circuit is same as before, only we add the additional DC supply voltage VBB. So from the analysis using Kirchhoff voltage law, so we can know that VBB equal to IB RB plus VBE. So after we simplify, we can get IB equal VBB minus VBE divided by RB, and then after we put the value, we can get IB is equal to 15 microampere, and then we can use the general formula IC equal to beta IB, and then after we put the value, we can get the 1.5 milliampere, and And then we can also get the VCE using Kirchhoff voltage law, where VCC equal to ICRC plus VCE, and then after we simplify, we can get VCE equal VCC minus ICRC, and then after we put the value, we can get VCEQ equal to 7.5 volt. And then we also can get these three value, that is VB from base to the ground, and then VC from collector to the ground, and then VE from emitter to the ground, and then we can get this value. So after that, we know that VBE is forward bias and BC is reverse bias. This is the circuit that BJT is operate in saturation region. The circuit is same as before, only we increase the voltage VBB from 1 volt to 1.49 volt. So after we analysis the circuit using Kirchhoff voltage law, we can get VBB equal to IBRB plus VBE, and then after we simplify, we can get IB equal to VBB minus VBE divided by RB, so we can get the IB is 39.5 microampere. IC is equal to beta IB, so we can get 3.95 milliampere, and then after that, we at the output loop we use Kirchhoff voltage law, and then we can get VCC equal to ICRC plus VCE, and then after we simplify, we can get VCE equal VCC minus ICRC, and then we can get VCEQ equal to 0.15 volt. So we also can get the base voltage, collector voltage, and VE voltage. So after we can get the value, so we can know that VE junction is forward bias and BC junction is forward bias. From the output characteristic of BJT IC versus VCE, so the Q point of transistor must be below than maximum power curve, maximum power dissipation curve, where the Q point must be below, and if the Q point is more than maximum power dissipation curve, transistor will be burned. This is the BJT specification, so which explain the parameter maximum value. For example, here collector current IC, the maximum current is 100 milliampere, and our beta or DC beta is 110 until 450.